Okay, so starting with kinetic energy. What's the usual indicator for that? What has to be changing in order for kinetic energy to be involved?
Speed.
Yeah. Energy of speed. Speed being distance over time. How much the position is changing divided by how much time passes. So it's going to have to involve speed somehow. And what else should it involve? Or do you have a formula for that yet?
It would involve mass.
Yeah, it's going to involve mass as well. I find it useful to think of kinetic energy as if we think of energy as how much work has been accumulated, since work is just a transfer of energy. Kinetic energy is a measure of how much work it would take to get something moving that fast in the first place. Like if you've got an object that's moving at some speed, if you assume it started from rest, it's going to take a certain amount of work, a certain amount of force applied over a distance to get it moving that fast in the first place. The faster it's going, the more energy it's going to take to make that happen. But also the more massive it is, the more energy it's going to take to get it up to that speed in the first place. However, just mass times velocity alone doesn't work. It turns out that we also need a squared on the velocity to get the units to work out right. In fact, if we take a look at the units here, what's the usual units of measurement for mass?
The units for mass?
Yeah. What do we measure?
Kilograms?
Yeah, kilograms. Mass is going to be measured in kilograms. And if speed is defined as distance over time, what would those be measured in?
Meters per second.
Right, so we've got meters per second. If you just multiply kilograms times meters per second, you don't get joules. It turns out joules is actually kilograms times meters squared over seconds squared. So in order to get the units to work out right, we need a squared on the velocity, so we get kilograms meters squared over seconds squared. And that alone isn't exactly enough either. We also end up having a 1/2 here. And that 1/2 is actually there for a reason. For a long time, I assumed that that 1/2 was experimentally determined. Like add this much energy, figure out how fast it's going, and you find that there has to be a 1/2 in the formula for the results to work out right, which is true. But you also can actually get that 1/2 from calculus as well. Do you recall anything from calculus that would turn a variable into 1/2 times that variable squared? Where have you seen something like that in calculus?
Would that be an integral?
Yeah, if you integrate this, the integral of v with respect to itself is 1/2 v squared. And that's actually exactly where this 1/2 comes from. The formula for kinetic energy is derived in the first place from taking the integral of mv with respect to v. And we're going to learn more about mv later on in 7b. That's a quantity called momentum that we're going to revisit later. But it turns out that there's actually quite a lot of formulas in physics and elsewhere that have something to a power and also divided by that power. Anytime you see that sort of format, that's probably because it comes from an integral in the first place. So this is often where extra fractions like this come from some sort of integration. Any questions on that so far? And as usual, we usually don't care how much energy it has. Sometimes we do. Like if you want to know how much work it would take to get it up to a certain speed from rest, then the amount of energy matters. But most of the time, what we care about is the change in energy. So how would you write out how much the kinetic energy is changing? What's the only piece of this formula that would actually be changing?
The speed.
Right, the speed. So the 1/2 m is a constant, and you can factor that out of the delta. But we still have delta speed squared. And we usually write the speed squared in parentheses just to emphasize that that means the final squared speed and the initial squared speed, and then subtract. So square the final speed, square the initial speed first, and then subtract to find the difference in squared speed. So that's how you'd find the change in kinetic energy, which could be interpreted as how much work do you have to do to make that change in speed. Any questions on that so far? And then potential energy is more of energy associated with position or orientation, or sometimes shape. Or more broadly, I would say it's the energy associated with certain forces. Certain forces related to position, orientation, or shape. For example, what's one type of potential energy you've seen so far?
Gravitational.
Gravitational. And gravitational potential energy is associated with the gravitational force. If you've got an object near a planet, it's experiencing a force towards the center of that planet. That's the force of gravity, that pull towards the center. But that force can also be associated with a potential energy. The object has a form of energy associated with its position relative to that planet and associated with that force. And you can think of this as, the reason why we call it potential energy is it's essentially energy that is stored up in the object's position. If you've just got some object, you're holding, just by holding it in place, you're exerting an upwards force to counteract the force of gravity. If you lift the object, you're applying a force as the object moves some distance. And what do we call force times distance?
Work.
Yeah, that's work. So by applying a force to the object as it moves some distance, you're doing work to it. That's a transfer of energy. But that energy isn't lost. The object now has more energy by virtue of being in this higher position. And you can get that energy back by letting it go, at which point that stored potential energy turns into what instead?
Kinetic energy.
Exactly. So a good way of thinking of potential energy is it's a way to store energy that has been invested as work using some sort of force associated with a position. And then you can get that energy back by allowing it to turn into kinetic energy. Any questions on that so far? So every potential energy is associated with some sort of force. Not every force has a potential energy associated with it though. Not every force allows work to be stored up. For example, friction. If I'm just sliding this marker along the ground or something, I'm applying a force to counteract friction, but I can't let it go and allow it to snap back. It's not storing up the energy. The energy is just lost, presumably turns into thermal energy, but it's not stored up in a useful way. So some types of forces have potential energies associated with them, allowing you to store up work. And the main ones we're going to be looking at, as was mentioned earlier, are potential energy of gravity associated with the gravitational force, and spring potential energy associated with a spring force. And potential energy of gravity, what's usually the indicator for that?
Height.
Yeah, you're lifting the object up to a higher height to give it more potential energy of gravity. So height, usually written as y, is going to be involved. Units of that, of course, being meters. What else would you expect to be involved in terms of how much work it takes to lift something up to a shelf? Other than just the height of the shelf, what else determines how difficult it is to lift the object up to the shelf?
Its mass.
Yes, the mass of the object. More massive is going to mean it takes more work to bring it up to the shelf. Mass being measured in kilograms. But kilograms times meters alone doesn't create joules. What else do we need in order to get the right units here? If we want joules, which is kilograms meters squared per second squared. What are the missing units?
Meters per second squared.
Yeah, we need an extra meters and an extra divided by seconds squared. Anyone know what those are the units of? Meters per second squared.
Acceleration.
Yeah, that's acceleration. Meters per second was velocity, how fast you're moving. Meters per second, or meters per second squared is acceleration, how fast your velocity is changing. And so we're actually going to have an acceleration here as well, usually written as g, which is the acceleration of gravity. So this g here basically represents how much gravity speeds up an object as it falls. As an object falls, it's getting faster and faster and faster. G is how fast the speed is changing as the object falls. So this works for a formula for gravitational potential energy. It gets the units to work out right. It turns out we don't actually need any extra multipliers. So just mass of the object times g, the acceleration of gravity on whatever planet you happen to be on, times height. Any questions on that so far? And if you are on or near the surface of Earth, gravity is, I think it's precisely something like 9.81 or 9.82 meters per second squared. For purposes of a lot of problems we're going to be seeing, we're just going to round that off to about 10 meters per second squared. In general, if you're going to be using a calculator for a problem, I would just use the 9.8 to be more precise. But if you just want a quick mental estimate, rounding it off to 10 is going to get you at least pretty close to the result. But keep in mind, 10 is just a very rough estimate. It's much closer to 9.8 meters per second squared. And of course, if you're talking about on another planet or on a moon or something, it's going to be a different value. But this is standard value near Earth's surface. Any questions on that so far? And again, usually what we care about is change. What's the only piece of this you would expect to change?
Why?
Yeah, the height could be changing. Presumably the mass of the object does not change. G can change if you're talking about going a very long distance, if you're like launching far away from Earth. But as long as you're not moving too far away from the surface of the planet, M and G can both be treated as constants. So delta potential energy is just mg delta y. Any questions on gravitational potential energy so far? And then spring potential energy, if you have a spring and you're stretching or compressing it, what's going to determine how much energy the spring has? What's our indicator there? Like if you just got a spring, if you just got this spring that's sitting there and nothing's attached to it and it's just at rest, presumably this spring has no energy. How would you invest energy into it? How would you store energy in the spring?
It would be determined by like distance from the equilibrium position. So like pushing or pulling on the coil.
Yeah. If this is equilibrium in the sense that if it's at this position, then there's no forces at all. But let's say you stretch it out. It has now been stretched some distance from equilibrium. Let's say some distance x. And that's usually what we're going to be using x for in this case. In this context, x represents distance from equilibrium. So if you stretch, then x is positive. If you compress, we usually treat x as a negative value. But it turns out that the spring potential energy is symmetric. If you stretch the spring from equilibrium, you're adding energy to the system. Or if you compress the spring from equilibrium, you're also adding energy to the system. Stretched and compressed are both high energy settings. So this spring, this stretched spring, has potential energy. And the reason for that has to do with work. In order to stretch it, you have to apply a force as it moves some distance. You're doing work to stretch it out. That work is stored in the spring as potential energy. You could now, for instance, tie off the spring, maybe tie it to a post here or something, and it now has this stored energy. Release it and it's going to snap back. The potential energy you stored in it turns back into kinetic energy. Or alternatively, if you compress it, you're storing energy into it. Then tie it off and it's stored energy. Cut the string and the spring snaps back, turning the potential energy into kinetic energy again. And it's always going to be pushing or pulling itself back towards equilibrium. The spring force is an example of what's called a restorative force. Restorative in the sense of trying to push or pull back towards equilibrium. If you stretch the spring exerts a force trying to pull back towards equilibrium. If you compress the spring exerts a force trying to push back towards equilibrium. Any questions on that so far? And there's a couple of useful formulas we can use here. One of them is the formula for the force of the spring. The force of the spring is, it turns out, proportional to the displacement. If you displace a spring a certain distance, it's going to cost, you're going to have to apply a certain amount of force just to hold it in place. If you want to stretch the spring 3 times as far, you're going to need to apply 3 times as much force to make that happen. The force that the spring pulls back with is proportional to how far it's been stretched or compressed. And anytime things are proportional, we can say one of them equals a constant times the other one. In the context of the spring, we call that constant the spring constant, which we usually just write as K. And that basically represents how sturdy or how strong the spring is. A very stiff, sturdy spring, like in an automobile suspension, is going to have a very large value of K. A very floppy spring, like a slinky, is going to have a very small value of K. And there's also one other thing we need in this equation. If you, let's say you stretch a spring to the right. You've displaced it to the right, X is positive. Which direction is the spring force in that case?
To the left?
Yeah, you stretch the spring to the right, the spring is pulling back to the left. Or if you compress the spring to the left, the spring is going to be pushing back to the right. The spring force is in the opposite direction from the displacement itself. How do we show that mathematically? What symbol should we use for in the opposite direction?
A negative?
Yeah, a negative sign. So this is our usual formula for spring force. The force caused by the spring, the pushback, is opposite of spring constant times X. This is usually called Hooke's law for forces on it, forces caused by a spring. And we can actually always convert a force formula into a potential energy formula. If that force has a potential energy associated with it, we can actually define potential energy based on force. And the way that's defined is potential energy is defined as the negative integral of force with respect to position. So we can actually build a formula for potential energy based on this. If we just integrate this, note that the negatives cancel out. So we just get integral of kx dx. K is a constant, so you can pull that out. What's the integral of x dx?
1/2 x squared.
Right, so we get 1/2 times k, a constant, times x squared. So this is actually where the formula for spring potential energy comes from. If you start with the formula for force of a spring, then take the negative integral of that, which is how we define potential energy in the first place, then you end up with 1/2 kx squared. So that's the formula we can use for potential energy of a spring. And note that if we were to graph this, what's the shape of that graph going to be?
A parabola for the potential energy?
Exactly. The graph of potential energy is going to be a parabola with the vertex at the origin. So that means, first of all, the potential energy is lowest at equilibrium. Equilibrium, if the spring is just at rest at equilibrium, or not even necessarily at rest, as long as it's at equilibrium at the moment, maybe it's passing through equilibrium. If the spring is at equilibrium length, then it's at its lowest possible potential energy. If you stretch the spring, you're increasing its potential energy. But also if you compress the spring, you're also increasing its potential energy. We have this complete symmetry here because x squared doesn't care whether x is positive or negative. So for this reason, we typically use absolute value of x as the indicator. Because x squared doesn't care whether x is positive or negative. It doesn't really matter whether x is increasing or decreasing. It matters if absolute value of x is increasing or decreasing. Are you getting closer to equilibrium or further from equilibrium? Same thing for kinetic energy. We usually use absolute value of speed as the indicator. Speed, we do sometimes assign a positive or negative sign to speed representing direction of travel. Is it moving forward or backwards or up or down? But since speed is being squared in the formula for kinetic energy, it turns out direction doesn't matter. Energy is a directionless quantity. So we don't really care about direction as far as energy is concerned. Any questions on that so far?
So Hooke's law does not have the 1/2 constant in front of it?
Right, Hooke's law for the force is just spring force equals negative kx. In fact, this is basically how we define K. K is defined as absolute value of force over displacement.
Would you use the absolute value of x for Hooke's law as well?
No, in this one, x actually, the sign of x actually matters. The whole point of the negative sign here is that if x is negative, then the force is in the positive direction. If x is positive, then the force is in the negative direction. You could say, for instance, that absolute value of force equals k times absolute value of x.
But that would just be the magnitude.
What was that?
That would just be the magnitude of the force.
Exactly. So this is true. This tells you how strong the force is, but it's kind of losing information. This equation includes a little bit more information because this one tells you not only how strong the force is, but also in which direction the force is pushing or pulling.
I see. Thank you.
Mm-hmm. For potential energy, though, the potential energy of the spring is always going to be positive. Well, positive or zero. I should at least say it's non-negative.
What would be an example of a non-restorative force?
Gravity would be an example. Gravity is not really pulling towards some equilibrium. Gravity is just pulling down all the time.
Okay. Okay.
If you look at it in the big picture, I guess you could say the center of the planet is equilibrium. But we're not really looking at in the big picture with the entire planet. We're just looking at locally. If you look at some region near the ground, then gravity is not pulling towards some equilibrium from all directions. Gravity is just pulling everything straight down.
Okay, thank you.
Mm-hmm. Friction would be another example. Friction's not really trying to restore some location. You could sort of say friction's trying to restore zero speed, is trying to bring the object to a stop. But friction isn't pushing towards some equilibrium location. Any other questions on these types of energy so far?
Yeah, I had a question about the spring constant. Mm-hmm. So a larger or a denser spring would have a larger K.
Yeah, or I would say a sturdier spring.
A sturdier spring with a larger K. I'm just confused because I'm thinking that a sturdier spring would move less when you oscillate it. So how does that translate to an increase in potential energy?
Potential energy is not so much about how much it moves when it oscillates. It's more about how much work it would take to bring it to that location in the first place. Like if you've got, let's say you've got a variety of different springs and you want to try taking each one of them and compressing it 1 centimeter. If you've got a very weak spring, it's going to be very easy to compress it 1 centimeter. So it's not going to take much work. If you've got a very sturdy spring, it's going to be a lot of work to compress it 1 centimeter. It's going to be more difficult. So larger spring constant means it takes more energy to get the same effect.
Oh, okay. That's the measure of, all right, the work needed to get back to equilibrium. Yeah. Okay.
Yeah, I tend to think of it as being like a difficulty level. Spring constant is how difficult it is to compress that spring a certain distance. Any other questions on that so far? And spring constant is generally going to be measured in newtons per meter because that's the units of force over distance. Newtons divided by meters. You can also write it as joules over square meters. Because if you just multiply top and bottom by meters, newtons times meters is joules, because that's a force times a distance, which tells you work. So you could write this as joules over square meters. So K can be written as newtons over meters or joules over square meters. It's just two different ways of writing the exact same thing. You could also replace joules with kilogram meters squared over second squared, cancel out the meters squared and get joules, or sorry, kilograms over second squared. So you might see it written in that format also. But these are just three different ways of writing the same thing. Newtons over meters, joules over square meters, kilograms over second squared. They're all the same thing. Any other questions on that so far? All right, let's try out an example then. Maybe a thrown object. Let's say you have a 5 kilogram object and you are starting, let's say you start 2 meters above the ground. And you throw this object upwards with some speed, some unknown speed. And let's say we want to know how fast you have to throw it so that it reaches a final height or a maximum height of, let's say, 20 meters above the ground. So we want this to reach 20 meters above the ground from the 2 meter starting height. And we want to know how fast you have to throw it to make that happen. One way we could accomplish this is using the same energy interaction diagrams we've been working with. From here to here, from initial instant of the throw to final instant of maximum height, what types of energy are changing here?
Kinetic energy and gravitational energy.
Yeah, we've got kinetic energy of the ball and I would say gravitational potential energy of the ball. Using our indicators, absolute value of speed and height. So is the ball's absolute value of speed increasing or decreasing?
As it goes up, it would be decreasing.
Yeah, presumably the ball is getting slower as it rises. I mean, that should match your general everyday experience with objects. You move an object upwards. As it's drifting upwards, it's going to get slower. So its kinetic energy is decreasing. In fact, we know, I guess we don't know its starting speed. But if we assume the final situation is when it reaches its highest location, what's the final speed if it has just reached its highest location?
20 meters off the ground.
That's the final height.
It would be 0 meters per second.
We should assume that it reaches a final speed of 0 meters per second at that instant. And of course, after that, it's going to start falling back down again. But in general, if it's reached the highest point, we should assume it has reached a complete stop. Because if the final speed wasn't 0, that means it hasn't reached the highest point yet. It's still on its way up. You could even look at this in terms of calculus. if you've got some function height as a function of time, think back to calculus. What do you do to a function if you want to maximize it? If you want to find its maximum or its minimum value?
You take the derivative and you set it equal to 0. And
exactly. You take the derivative, in this case, derivative with respect to time, because height is a function of time. And you set the derivative equal to 0. But what is the derivative of position? Derivative of position over time, what do we call that?
Velocity.
Exactly. So mathematically, this is why we're setting the final speed equal to 0. Velocity or speed is the derivative of position. And the way you maximize a function is by setting its derivative equal to 0. So if you want to find the maximum or minimum value of position, set its derivative, which is speed, equal to 0. If we can find an instant in time when the speed is 0, that's going to be a maximum or minimum value for position. Any questions on that so far? And we also know an initial height is 2 meters above the ground. So is the height increasing or decreasing?
Increasing.
Yeah, height has increased, so potential energy of gravity has also increased. By the way, there's no reason we have to call ground level y equals 0. It's often convenient to do so, but instead of calling ground level y equals 0, you could call, for instance, the initial location of the ball y equals 0. So you could say y initial is 0, and then y final would be 18, because that's 18 meters above that location. So all these heights are really just relative to whatever coordinate system we're using. You could even use, like, let's say this happens to be 100 meters above sea level. You could say sea level is height 0. The ball is launched from height 102 and reaches a height of 120. What you call the y values doesn't really matter as long as you're consistent about it. The important thing is the difference, that the final height is 18 meters higher than the initial height. So it looks like those are the only energies that are changing here. And would we treat this as an open system or a closed system?
It depends on if you're including Earth as part of your system.
Yeah, and I think we kind of are here, because what type of energy are we already including that sort of implies that?
The gravitational potential.
Yeah, potential energies, in fact, forces in general and the potential energies associated with them are all about relations between pairs of objects. If there's only one object in existence, there isn't really any forces or potential energies to consider. They're all about interactions between pairs of objects. In this case, potential energy of gravity is about the interaction between the ball and the Earth that's causing the gravity. With no Earth, there would be no gravity on the ball. And with no ball, the Earth would have nothing to exert gravity on. So gravity is all about the interaction between massive objects. So as long as we're including the Earth in our system, which I think is sort of implied by the fact that we're talking about potential energy of gravity, then we are including everything here. The only other exception I would consider is if there's air resistance. If we have to consider the fact that the ball is pushing through the air in order to move, then air resistance would be applying a force as the object moves, and that's work. So if air resistance is significant here, we would have to treat this as an open system with work leaving the system because of air resistance. But generally, air resistance only applies to very, very lightweight objects or very spread out objects or very, very fast moving objects. Since the ball is presumably fairly compact, fairly heavy, and not moving ridiculously fast, I think we can assume that the air resistance is small enough to not worry about. And so we'll treat this as a closed system. So we should be able to write out our conservation of energy equation. In a closed system, these changes should add up to 0. We can fill in the formulas we were just looking at, 1/2 m delta v squared. And then mass times gravity times delta height. And those add up to 0. And by the way, what shows up in every single term here?
Mass.
Yeah, mass shows up in every term. And if mass shows up in every term in the equation, we can actually just divide both sides by mass and get that to cancel out. Note that we wouldn't be able to do this if there was another term that didn't have mass. For example, air resistance would not have mass in it, so we wouldn't be able to cancel it out. Or if there had been a spring involved, the spring force, or the spring potential energy, 1/2 kx squared doesn't include mass. So if there was a spring, we wouldn't be able to cancel out mass. But as it is, we just got 1/2 times, and I'll go ahead and fill in final minus initial, v final squared minus v initial squared, plus g times y final minus y initial equals 0. And since mass no longer appears in this equation, what does that tell you about mass in this situation?
It's irrelevant. It doesn't affect the speed that the object's going to fall.
Exactly, completely irrelevant. It doesn't matter if this was a 5 kilogram object launched at this speed to get to 20 meters, or a 500 kilogram object. If you've got some object that you want to get from 2 meters to 20 meters, the speed you have to launch it at doesn't depend on the mass of the object at all. Of course, the more massive object is going to be more difficult to get to that speed when you're throwing it. But if you throw it at the required speed, it's going to reach 20 meters, no matter how massive it is. What else can we do here? Generally, I would recommend solving algebraically before plugging in numbers, but I noticed that one of the numbers is 0. That is often useful to plug in right away. If we fill in 0 for v final, then we're really just left with 1/2 times negative v initial squared plus g times the difference in height equals 0. And now we can solve this for v initial pretty quickly algebraically. Just add v initial squared over 2 to both sides. Multiply by 2. And then what would be one last step here?
Take the square root.
Yeah, take the square root of both sides. And usually I would include a plus or minus when you take the square root, but plus and minus here signifies direction. And we already know the ball is going to be thrown upwards. So I don't think we need to worry about the plus or minus here. But what we now have, by doing this algebraically with variables instead of plugging in the numbers yet, instead of just getting a number, we get a formula. If you want to get an object from height y initial to height y final, this formula tells you the speed you'd have to throw it at. And now we could plug in the numbers. Square root of 2 times, let's go ahead and round off gravity to 10 as an approximation. And y final minus y initial, that'll be 20 minus 2, so that's 18 meters. So we get 20 times 18 would be 360. And note that the units, we get meters squared over second squared, but then we're taking the square root. So that just becomes meters per second. So square root of 360 meters per second. We could also split that into square root of 36 times square root of 10. So that's 6 square root of 10 meters per second. So that tells us how fast it's going to have to be thrown. 6 times square root of 10. So about 19. If you throw this at about 19 meters per second straight up, it will reach approximately from 2 meters to 20 meters. Any other questions on that? So this energy interaction diagram approach works really well if all you care about is initial value and final value. It doesn't really tell you anything about what's happening in between though. If you wanted to find, for instance, well, now that we know this is the launch speed, how fast was it going when it was halfway up? Or how fast was it going when it reached 19 meters? Or how high was it when it had slowed down to 3 meters per second? If we wanted to know answers like that, we'd have to run through this whole problem all over again. But one of the advantages of drawing it as a graph instead, if we make a graph of height versus energy, is that we can look at all those in-between values more visually. So let's try drawing a graph of this as well. Now that we know this is approximately 19. The idea is we're going to be making a graph of height versus energy. And I find it useful to, at least for the first few times you do this, it's a good idea to write out a data table to keep track of the information. We care about height. We care about potential energy of gravity. We care about kinetic energy. And we also care about total energy. So generally, I would write out a data table with whatever variable you're using for position, in this case, y. All the types of energy that you care about, in this case, just potential energy and kinetic energy. And also include a column for total energy, because we care about how much energy the system has. What are the important heights we care about here?
$2 meters and 20 meters.
Yeah, 2 meters, 20 meters. I'm going to fill in a couple other values as well. Let's say 0 to, let's say also 10, 15, and 20, just to fill in some of the in-betweens. We can calculate potential energy directly because we know that the potential energy is, what's our usual formula for potential energy?
mg delta y.
Yeah. Although since we're not looking at delta here, we're looking at what's the actual potential energy. We'll leave off the delta and just use mgy. M is 5, G is 10, so mg would be 50. So 50 times y, meaning we can just multiply each of these by 50. 0 times 50, 2 times 50, 10 times 50, 15 times 50, and 20 times 50. So we can quickly fill in all of these potential energies just by filling the y value in for the formula for potential energy. And we can graph that. We can now just mark these values on a graph. We know we need to go up to 1,000. And if we start plotting these points when y is 0, and note that the ball never actually touched y equals 0 in the interval we're talking about, but we can still plot it on the graph as a theoretical data point. 0, 0, 2, 100, 10, 500, 15, 750, 20, 1,000. So these points represent information about potential energy of gravity. And what shape do these seem to form?
It's linear.
Yeah, this is linear. Because the original equation, just mgy or 50y, input or output equals 50 times input. Since the output energy is just a constant times the input height, that's going to be a linear function passing through the origin even. So the graph of potential energy is going to be linear because it's a linear equation, a linear function. Kinetic energy is going to be a little more complicated though. We can't just use 1/2 mv squared because this is not a graph of speed, it's a graph of height. So we can't just use a standard formula for kinetic energy, But what we can use is the fact that we know the kinetic energy at the top. At 20 meters, we want the speed to be 0. So at 20 meters, we want the kinetic energy to be 0, because it has to come to a complete stop at that instant. And this is a really important height here, 20 meters, because at this height, we know the potential energy and the kinetic energy. If you know the potential energy and the kinetic energy, what can you find?
The total energy?
Exactly. We can just add those up. If there's any single location where you know all the types of energy involved as their values, add those up and you get the total energy. And in a closed system, what should we assume about the total energy?
It's constant.
It's constant. If it's 1,000 joules here, it's 1,000 joules everywhere. And so if we just graph a constant function, what would that look like on the graph? If it's 1,000 here, and 1,000 here, and 1,000 here, and 1,000 here, what shape do we draw?
A straight line.
Yeah, specifically a flat horizontal line. So total energy is just going to be a flat line. And with that, we now know the potential energy everywhere, and we know the total energy everywhere. So how can we find the kinetic energy everywhere?
You could subtract the potential energy from the total energy.
Sounds good. 1,000 minus 0 is 1,000. So at height 0, we'd have 1,000 joules of kinetic energy. 1,000 minus 100 is 900. So at height 2, we've got 900 joules of kinetic energy. 1,000 minus 500 is 500. So at height 10, we've got 500 joules of kinetic energy. 1,000 minus 750 is 250. So at height 15, we've got 250 joules of kinetic energy. Fill in the in-betweens, and it looks like this forms a straight line also. Because we don't really have a formula for kinetic energy in terms of height, but we do know that kinetic energy is E total minus potential energy. So as the potential energy increases, the kinetic energy has to decrease at the same rate. If there's only two types of energy changing, their graphs should be mirror images of each other. And now with a graph like this, we can predict what's the kinetic energy going to be at any height. If we want to know how fast is the ball going at height 15, we can look up the kinetic energy, set that equal to 1/2 mv squared, and solve for v. Or if we want to know what speed it was launched from, look up the kinetic energy at height 2, that looks like 900, set 900 equal to 1/2 mv squared, solve for v, and you've got the speed at that instant in time. So this shows all the in-between values. It's not exactly as precise as working it out algebraically. You can't really see the exact values everywhere on the graph, but it gives you an excellent visual understanding of what's going on at all the instants in time in between. As the ball goes up, increasing its height, it's gaining potential energy, losing kinetic energy, keeping the constant same total energy. So that's a very complete picture of all the types of energy that are changing and how they're changing in the in-between regions. And we're going to be using this same approach for spring potential energy, and also later on, the potential energy of individual molecules interacting as they vibrate. Any questions on that?
Yes. So if I wanted to calculate, for example, the kinetic energy at y equals 17, that's possible with this graph, right? All I have to do is just set the values in, punch the values in.
Yeah, and conceptually, you could just look it up on the graph and say 17 here, that looks like about somewhere around 200. Or you could be more precise by using the data table. 17 times 50 would tell you the potential energy. Subtract that from E total to find the kinetic energy. And then if you wanted to convert that to speed, set it equal to 1/2 mv squared and solve for v.
Oh, okay. So there's a bunch of different ways to go about this kind of. Okay.
Yeah, the graph gives you a quick visual idea. It helps you develop more of an intuition for how it's changing and why. And then the data table and working it out numerically can give you more precise results. And I think it's a good idea to do both. Try drawing out the data table and the graph, compare the information, and make sure you can wrap your mind around how these are just two different ways I'm displaying exactly the same information. Any other questions? All right, have a good weekend, and I will see you next time.
Thank you.
You're welcome.